Welcome to the deep dive. So you sent us some really interesting material today. It's not the usual research papers, but something quite practical. Practice scenarios from the AWS Solutions Architect Professional Certification, SAP-C02, right?
Exactly. Yeah, this is definitely the deep end stuff. These aren't simple, what is S3 questions. They're complex real world problems where you've got cost, security, performance, compliance, all pulling the architecture in different ways.
Right. And our mission here is, well, it's pretty simple. We're using these tough scenarios as a shortcut, really. By breaking down the why behind the solutions, we can jump straight to understanding the critical architectural trade-offs people are making in the cloud today.
It's a fantastic way to accelerate understanding. And just to give you a sense of the depth required, the actual exam is, 180 minutes for 75 questions. You really need to know the services inside out, especially those features for policy enforcement or, massive scale.
Okay, so let's dive in. We can group the first few around, let's call it securing the perimeter, networking and access, stuff about locking things down at the network level. First one, centralized routing. Big company using AWS Transit Gateway, TGW, to connect everything, including their on-prem data centers. The rule is strict. On-prem traffic can hit production VPCs, but absolutely cannot reach development VPCs. And critically, this block needs to happen at the network routing level.
Yeah, this is a classic. People often reach for, say, a network firewall or maybe security groups first. But you see, that's more about inspecting traffic after it's already been routed somewhere.
Ah, okay. So why is that the wrong way to think about it here? I mean, if the requirement is enforcement at the routing level.
Well, because if the route actually exists, the traffic can still try to flow, right?
Yeah.
Even if a firewall drops it later. The really clean, definitive way to enforce this kind of network isolation is to make sure the unwanted route simply isn't there in the first place. It's about segmentation.
So using the transit gateway itself.
Exactly. The key nugget here is using the TGW's own segmentation capability. You create separate route tables within the transit gateway.
Okay, so like production VPCs get attached to one route table that can see the on-prem connection, and the development VPCs get attached to a different route table that can't see it at all.
Precisely. You control how the routes propagate between these tables. This enforces that isolation right at layer 3. It's much cleaner, much more robust than relying on, say, a layer 7 firewall rule later on.
That distinction, routing enforcement versus inspection, that's really important. Okay, let's look at the second networking challenge. This one involves integrating a specific kind of third-party tool, like maybe an intrusion prevention system, doing deep packet inspection. And the critical bit, it needs asymmetric routing.
Right. That term, asymmetric routing, that should immediately ring a bell. It means traffic absolutely must go out through the same appliance it came in through. If you try to force that with standard load balancers, especially when you scale out those appliances, things get very messy, very unstable, very quickly.
Makes sense. Standard load balancing would just spray the return traffic across any available appliance, wouldn't it?
Yeah.
So is there a specific AWS service built for this? For inserting these kinds of appliances and handling that required flow symmetry?
There is. It's the Gateway Load Balancer, or GWLB. It works down at the network layer, layer 3, and it's designed specifically to maintain that flow stickiness. It ensures both directions of a single network flow always transit the same inspection device.
So if your security appliance vendor says asymmetric routing needed, GWLB is pretty much the go-to answer.
It's really the only practical and scalable option for integrating those stateful third-party network virtual functions, yeah. Definitely GWLB.
Excellent. Okay, let's wrap up this sort of governance section with identity management. We've got a big company scenario again. Employees use on-premises Active Directory, ADD. They need AWS console access. And crucially, they need to assume different AWS roles based on their existing AD group memberships. Big constraint. No creating thousands of individual IAM users.
Yeah, managing individual IAM users for potentially thousands of employees, that's just an operational nightmare. It doesn't scale, it's error-prone. The solution really has to leverage the existing identity source, the on-prem AD.
So what's the standard AWS way to bridge that gap?
That would be implementing AWS Single Sign-On, which you'll now see mostly referred to as IAM Identity Center. You basically connect Identity Center to your corporate AD.
Okay.
And it handles the whole federation process. It authenticates users against AD, and then importantly, it maps their AD group memberships directly to specific IAM roles within your AWS account. So you get that granular control without managing duplicate users.
Got it. Centralized identity managed via the existing AD.
Yeah.
Okay, let's switch gears. Phase 2, scale and survivability. Thinking about data, handling huge load, and making sure things stay up. So first up, a scaling crisis. High-traffic website currently struggling with a manually sharded Amazon RDS MySQL database. They need to migrate to a single database system, no manual sharding, that can handle millions of requests per second.
Wow, okay. Millions of requests per second and explicitly getting rid of manual sharding.
Right.
Yeah, that immediately tells you you're probably hitting the limits on what even a really powerful relational database like Aurora can comfortably handle, at least without significant operational overhead. Managing those manual shards just becomes unworkable at that kind of scale.
So if they're willing to make some trade-offs, maybe like less complex query patterns or different consistency models, perhaps, in exchange for just raw scale, what's the obvious architectural path?
The move there is almost certainly to Amazon DynamoDB. It's a fully managed serverless NoSQL key value store. Its entire design philosophy is built around horizontal scaling to handle, well, pretty much arbitrary levels of throughput automatically.
Right.
You essentially trade the complexity of SQL and relational models for the operational simplicity and near infinite scale of a managed NoSQL service. All that sharding and partitioning complexity just disappears into the managed service.
Makes sense. A fundamental shift needed for that level of scale. Okay, sticking with databases, but shifting focus. Global reach. We have an Amazon Aurora MySQL database, doing great, but it's only in US East. Users all over the world, Asia, Europe, South America, are getting really slow load times, need to fix global read performance without messing with the primary write performance in US East.
Yeah, that's just physics, right? Network latency across continents. The data's just too far away from most users. So architecturally, you have to bring the data closer.
And for Aurora specifically, is there a built-in way to handle that kind of global read distribution?
Yes, there is. It's called an Aurora Global Database. With this setup, you deploy secondary Aurora clusters, essentially read-only clusters, in other AWS regions closer to your users worldwide.
So users in Europe hit a European replica, users in Asia hit an Asian replica.
Exactly. Those replicas handle the local read traffic with low latency. Meanwhile, the primary database in US East continues to handle all the write operations, maintaining consistency. It's a very clean way to separate read scaling geographically.
Got it. Okay, now for a classic trade-off. Disaster recovery. Critical application needs an RTO recovery time objective of 1 hour and an RPO recovery point objective of 15 minutes.
Okay, let's quickly define those just to be sure. RTO, how fast you need to be back up and running after a disaster hits. 1 hour here. RPO, how much data loss is acceptable measured in time back from the disaster. 15 minutes here. Those are pretty demanding targets.
They are. But here's the kicker. They have to hit these targets while keeping the ongoing cost in the secondary failover region as low as absolutely possible.
The cost constraint. Okay, so we're balancing recovery speed against operational expense. A full hot standby where everything is running identically in the DR region would easily meet the RTRPO, but it's the most expensive option day to day.
Right, essentially double the infrastructure cost.
Pretty much. On the other end, you have simple backup and restore. Lowest cost, sure, but restoring potentially large databases and provisioning all the compute, that's almost certainly going to blow past the 1 hour RTO. It often takes hours.
So neither extreme really fits. What's the middle ground? The strategy that hits that sweet spot, meeting the RTOPO, but minimizing the idle cost.
That would be the Pilot Light strategy. With Pilot Light, you keep only the absolute essential core components running in the DR region. Crucially, this includes the data replication, maybe replicating the database continuously to meet that tight 15-minute RPO.
Okay, so the data is current.
Right. But the expensive, scalable compute resources like the large EC2 auto-scaling groups or the EKS worker nodes, those are kept either turned off or running in a very minimal scaled-down state. You save a lot on cost day to day.
And then if disaster strikes?
You trigger automation to rapidly scale up that compute layer, connect it to the already replicated data, and bring the full application online within that 1 hour RTO window.
Makes perfect sense from a cost perspective. But what about complexity? Does Pilot Light add more moving parts or risk to the actual failover process compared to, say, a warm standby where more stuff is already running?
Oh, absolutely. It definitely increases the complexity and relies heavily on robust automation and well-tested runbooks. You have to be confident that the compute layer will spin up correctly and quickly integrate with the database within that hour.
Right.
A warm standby, where maybe the application servers are running but scaled down, is simpler to fail over to, less automation dependency perhaps. But you pay more for having that infrastructure idling. It's a very direct trade-off. Cost versus operational complexity and failover risk.
Great breakdown. Okay, let's move into our last section. We'll call this Phase 3, mandates and money. focusing on compliance rules, governance, and of course, cost optimization. First, a strict compliance requirement. A central security team needs all VPC flow logs and CloudTrail logs stored centrally. Fine. But they must be in a write-once format for 10 years. And here's the really tough part. They must not be changeable or deletable by anyone, and they explicitly call out, including the root user of the central logging account.
Whoa, okay. That last part, including the root user, that's the key constraint here. Normally, you might think a strong S3 bucket policy or maybe an SCP, a service control policy, could lock things down. But the root user in an AWS account generally has ultimate power and could, in theory, override or remove those policies.
So we need something stronger, something designed maybe for external regulations that even overrides AWS's own internal admin hierarchy. A true worm, write once, read many storage solution.
Exactly. The only AWS feature designed to provide that level of absolute regulatory-grade immutability, even against the account's root user, is S3 Object Lock, specifically used in compliance mode.
Okay.
You enable Object Lock in compliance mode on that central S3 bucket, set the 10-year retention period. Once that object version is written and the retention period is locked in, nobody, not even root, can delete that object version or shorten the retention period until it expires naturally after 10 years. It provides that guaranteed, legally defensible persistence.
That's a powerful control. Really changes the game for critical logs. Okay, let's shift from compliance mandates to operational costs, a common headache. Big data lakes. We've got petabytes of uncompressed JSON data sitting in S3. People are querying it using Amazon Athena, but the query costs are sky high because Athena scans the whole file every time.
Yep, classic Athena cost issue. Athena's pricing model is based directly on the amount of data scanned per query. And scanning petabytes of raw JSON is incredibly inefficient. JSON is row-oriented, so even if you only need data from one or two columns or fields, Athena often has to read through the entire row, the entire file structure. That inefficiency translates directly to big bills.
So the fix here isn't necessarily to ditch Athena, but rather to change the data itself to make those scans way more efficient.
Precisely. The standard architectural solution is to pre-process that data. You typically use an AWS glue job, that's the ETL service, to convert the raw JSON data into a compressed columnar format. The most common one is Apache Parquet.
And why Parquet?
Because columnar formats like Parquet store data by column, not by row, this means Athena can be much smarter. If your query only needs 2 columns out of 50, Athena can read only the data for those 2 columns and completely skip the other 48. Plus, Parquet usually offers good compression.
So drastically less data scanned per query.
Dramatically less, often 80%, 90%, sometimes even more reduction in scanned data volume. Yes, running the glue conversion job costs something, but the savings on the downstream Athena queries almost always make it hugely worthwhile, especially at petabyte scale.
That's a critical optimization for any large-scale data lake.
Yeah.
Okay, 2 more quick ones. First, self-service governance. How does a central IT team let development teams provision their own infrastructure? VPCs, EKS clusters, RDS databases, from a kind of pre-approved menu, ensuring everything stays compliant with company standards.
Right. You want to enable developers but maintain control. You need a service that acts as both a catalog and a gatekeeper for standardized templates. The purpose-built AWS service for this is AWS Service Catalog. Central IT defines and publishes products. These are essentially pre-configured CloudFormation templates representing approved architectures. Developers can then browse the catalog and launch these products themselves, self-service style, knowing they're automatically compliant, without needing manual reviews for every single deployment.
Got it. Governance through curated self-service. And finally, let's touch on storage for containers. An application's been containerized, moved to Amazon EKS. It needs persistent storage, but it also needs to be shared file storage. Multiple pods, maybe running on different nodes, need to read and write small files concurrently to the same file system.
Key phrase there, shared file storage. That immediately rules out things like Amazon EBS volumes, the block storage, because typically an EBS volume can only be attached to one EC2 instance, and therefore usually only pods on that single EKS node at a time.
Right. You can't easily share an EBS volume across multiple nodes for concurrent write access. So what's the managed AWS service that does provide that scalable shared file system experience suitable for containers?
That would be Amazon Elastic File System, or Amazon EFS. EFS provides a managed NFS network file system service. It's designed to be mounted concurrently by potentially hundreds or thousands of clients, including EKS pods running across many different EC2 nodes. It gives you that scalable, shared, persistent file access needed in many containerized applications.
If the whole promise of the cloud, initially at least, was about agility, about moving faster, how much centralized governance is the right amount? How much standardization using tools like Service Catalog can an organization enforce before it starts to maybe stifle the very innovation it wanted to unlock by going to the cloud?
That's a great question, finding that balance.
Yeah, something for you to think about until our next deep dive.